Happy to be here today to talk to you about type-safe machine learning orchestration with Flyte and Pandera. Before I jump in, my name is Niels Bentielen. I'm a machine learning engineer at Union AI, where we're building what we think are next-generation tools for machine learning operations. A little more background about myself. I have a background in biology and public health. I kind of fell in love with coding and data science and machine learning, and have now found myself building tools to make DS and ML practitioners more productive. So the crux of this talk is that type safety is a critical feature of orchestration tools that deal with data and machine learning. And just to level set with everyone, I'm maybe preaching to the choir here, but just to set a baseline, types define the set of values that data can take, but they also define the domain of operations that we can perform on that data. So if you consider the set of integers or strings, these are infinite sets, but here are some examples. Depending on the programming language or mathematics that you're using, adding two integers is well defined. 1 + 1 = 2. However, the operation of adding 1 plus the string a is undefined. And similarly, if you try to compute the mean over a collection, a list of integers, that's also well defined. The mean of 1, 2, 3 is 2. And unless you're using some kind of deep learning vectorized representation of strings in some embedding form, the mean of A, B, A, C is similarly undefined. So types can be simple, ints, strings, floats, things you're probably all familiar with. They can be more complex, like lists of ints, dictionaries mapping strings to floats, dictionaries mapping strings to list of floats, etc. And so to give you maybe a more real world but still kind of toy example, let's look at housing. This is the California housing dataset. You can access it on sklearn. It's one of the built-in datasets. And it's a dataset containing about 20,000 instances where each row in this tabular dataset is a district in California, and each variable, each column, is an attribute about this. And typically people use this in regression problems to predict median house value. I think it's in there somewhere. So if we look at the first set of values, just eyeball the first set of values of this dataset, you can already, as a human being who programs, you may program, you may have seen this data set before, you know what floats are. You can see that you can kind of start inferring what the types are. So all of these columns are floats. But if you know a little bit about the world, you can also say the range of latitude is between -90 and 90, and the range of longitude is -180 to 180. And if you look at the rest of the variables, it's kind of meaningless to have negative number of average bedrooms. So, okay, these are floats, aggregate values per district, and they have to be positive. So this is all kind of swirling around in your mind. And if you extrapolate this to more complex data that changes, something that isn't static in a toy data set, we all can know, if you are a data practitioner in some form or another, you know that enforcing and maintaining data quality is very challenging. And since this is a talk about ML ops, I'll tie this problem to problem number 2, which is production machine learning has a complexity problem. You might be familiar with this graphic. I think it was in a paper that Google put out a few years ago about technical debt incurred by machine learning systems. And I think this is probably well before the sort of maturing ecosystem of ML ops tools and data tools that we have today. But really the main point of this figure is to say, the ML code in that little black box is just a small piece of the ML system puzzle. So you have data collection, data verification, monitoring, all these pieces. Now, how do I know if these components are compatible? You might write Python code or whatever language you're using. You might write all these pieces in modules, and you'll connect them after the fact into your own pipelines. But how do I actually know whether they fit together nicely? And to answer this question, I'm going to go back to the very basics of programming, of a program taking some inputs and producing an output. So in a machine learning training module, your input might be a collection of features and labels, so pairs. And your program might be a learning algorithm that learns how to map those features to those labels in supervised learning. In this case, your output is a model artifact. And this is a model artifact that you can use in another setting, namely serving or prediction, right? So now your model, which is the output of this first pipeline, becomes the program of your inference or serving pipeline, which takes in input, which is the features, and output, which is the predictions that you'll use in your downstream business case. Now notice we can also say a few things that are implicit in this diagram, which is the features in the original input feature label pairs. That needs to probably be the same type as the features going into this serving pipeline. So hence all the feature store kind of products that you're seeing now, feature store tools. So really the premise of my talk, the thing that I want to convince you of if you're not already, is that strongly typed interfaces unlock static analysis capabilities that push many potential errors from the runtime context to the compile time context. And I'll define these as I go and as I talk through my next points. But my main point here is that if you have strongly typed interfaces, when you combine that with a few other features I'll show you later, you actually can enjoy a lot of benefits. And these benefits I'd like to talk about in terms of what, as a practitioner myself, what are the properties of an orchestration pipeline that I would like to have. So I would like, as a human being or machine, to be able to tell what the component types, input types, and output types are. So, I don't know if you've heard this quip before, but if there's no type system or type annotations, you're emulating a type system in your brain. You're trying to say, oh, what is this X? I don't know, it could be anything, with Python's duck typing, which got it really far. This is sort of a different philosophy of explicitly stating your types, even though there might be, you have a union of many different types. I also want it to be reproducible. So if an error occurs at the interface boundaries of my different components, I want to be able to reproduce it. And I want the guarantee that if the error occurs, I can rerun it and then debug it, locally. There are also some nice efficiency gains that you can get in combination with other features like caching. So if I want to determine whether I should hit the cache or recompute the value of some component, some function, I can first check for changes in the function signature before checking the actual values. And in terms of parallelization, before I try to concurrently apply a function to some collection of inputs, I can check whether the type signatures match. Now, the last two properties I'll talk about is I want to be able to, when a pipeline fails, to be able to see, pinpoint the cause of the error and understand how to address it. And finally, in a related way, I can understand how some downstream artifact came to be by looking at the processes, upstream processes that produced it. So here comes Flyte, which is a data and machine learning aware orchestration tool with type safety built into multiple layers of the software stack. With Flyte, you can easily compose workflows using tasks as building blocks. You pip install it. Here I'm defining just 3 tasks. They're just functions. You decorate them with at task. If you've seen other orchestration tools, this should look very familiar. I think we're sort of converging to on the similar syntax. And then the workflow at the bottom looks kind of like a function, but in Flyte it's actually a DSL. It's a graph that compiles into into some other format that I don't want to get into in this talk, but it basically constructs a DAG based on the function and the function invocations with the inputs and the outputs. So let's return to our California house price data set. We're going to formulate a regression problem here with a target of median house value at the very bottom, and with all the other variables as features. So this is an actual Flyte DAG. I'll show you the code in a second, but this is a high-level overview where, see if I can use this. Boom. We're first grabbing data. We're then summarizing the training and test data. So the get data set will actually produce your train and test partition. You're going to train the model in the training partition and then evaluate the model on both train and test partitions. Say you want to assess the degree of overfitting. Now, before I get into the code, I'm just going to tell you what types we're going to use. So these are kind of like the type building blocks that our task building blocks are going to use. In the top, you see a data set. This is all Flyte syntax, and it just uses regular Python constructs. So we're saying the data set is a data frame with these fields and these types. This is not a type, but this is just a global variable that just says what the target is. One part of our pipeline is going to split our data into training and test partitions. And the training result will be a ridge regression model with training mean squared error and test mean squared error. Finally, in the bottom are hyperparameters to the model. So here's an alpha value for regularization. Cool, so now we have our types. We're going to use those types in defining our tasks. I'm not going to go through laboriously enumerating all these tasks, but as you can see, all of them have type annotations, both inputs and outputs. Flyte will not know what to do with inputs that are not typed. It will know what to do with the untyped output. It's just kind of a none, no op, basically. Now, we've defined our tasks. Let's put it all together into a workflow. And it's pretty readable, I would say. But this is the thing that Flyte compiles into this DAG. And because Flyte is strongly typed, we can auto-generate strongly typed launch forms. So this is a launch form on the Flyte UI for launching this training workflow. As you can see here, the model hyperparameters, it knows the default I set for the meaning of life for the random state. Thank you for that. And we didn't set a default for the alpha value, so you're going to have to set that. I was talking about other features that work well with this. So each task you can think of as a containerized unit of work. And that has really nice reproducibility guarantees. So as long as your task is idempotent, you're not relying on some random, maybe you're setting your random state within the task, you can be guaranteed that your task is completely reproducible with all its dependencies, source code, etc. Now, I'll get into some of the kind of debugging benefits here. So Flyte will barf if the types don't match. So here I've intentionally changed the dataset input type of train model to a dictionary. And Flyte says, well, I don't know how to convert this data frame schema type into a dictionary. So, fix it before I even launch the workflow or put it into production. But obviously, you can't always catch everything because within that task function body, there could still be exceptions. So the local debugging experience is, because tasks are just Python functions, you can just run them locally. And in your new unit test suite, you can try to catch data corruption or other types of errors. But even in the case that those kinds of errors went unexamined and you've put something into production, Flyte will happily tell you where exactly that error occurred. It'll give you a nice error message. This is the same one we got locally, that I've intentionally removed this latitude column. To cache the outputs of your tasks is quite straightforward. You add the cache equals true flag into the task decorator, and this cache version gives you control over when you want to invalidate it manually. So if you've ever been in the situation where you're running a model and it's taken a week to run, and you're like, oh yes, I'm looking forward to the results, and then your evaluation module had a bug in it. Well, this is the error. The thing you can do is you can just fix the bug on that last component, relaunch your workflow, and this is an indicator in the UI that says all the previous components in this pipeline are cached. They didn't change. The inputs didn't change. So there you go. I'm going to start right where I left off. Also, if you look at this code, if you're thinking in Python, you're thinking that these two calls to summarize data will happen sequentially, and these two calls to evaluate model will happen sequentially. But that is not the case. When you put this, register this, deploy this to a Flyte cluster, this will actually both be called concurrently. So these two will happen around the same time, and these two will as well, as long as there are the resources available for it. And here, static type checking applies to these parallelized invocations of a task. So if I were to change the summarized data type from a data set to a dictionary, we see a familiar type error here saying, hey, I'm calling summarized data set on this trained data set, which is a data set, but it's actually expecting a dictionary, so you better fix that. Now, in terms of data lineage, right, the Flyte UI gives you the capability, like many other orchestration tools, to be fair, that say you have a mean squared error evaluation metric, and I'm curious, okay, what were the hyperparameters, what are the artifacts that produced this metric? I can look at the inputs that went into it. So this is one of the trainer test partition. This is the model, and this is the S3 path that contains these artifacts, that stores these artifacts. And I can go upstream into the upstream processes and do the same thing, inspect the inputs and outputs, see what parameters that produced the data set, etc. Cool, so I've basically thrown a bunch of features at you that Flyte does. But what about data types for machine learning? So this is where Pandera comes in, and I think I failed to mention earlier that I am the author of Pandera. It's an open source data validation tool that's kind of, I hesitate to use the word Pythonic, but I'll say it anyway. I've kind of tried to design it to be as Pythonic as possible, where you I'll show you in a second how intuitive it is to use. But the way I frame it is it's a statistical typing and data testing library for data frames, providing tools for defining types for complex data containers, and then also unit testing your pipelines with them. So there are these two terms, right? Statistical typing and data testing. I think they're worth getting into. So Statistical typing is extending the primitive data types to have semantics about collections of that type. So if you consider a single data point, right, in our example, we have latitude, longitude, and some other features. What can we say about this single data point? We can say what the primitive data types are. We can express some kind of constraints like value ranges, allowable finite set of values, a regex string match, nullability. However, if you look at a collection of data points, first of all, you can apply those atomic checks at scale. So if you're using something like Pandas or Modin or PySpark or something, you can then apply those atomic checks, to very large data. But something you can't do with just with the single data point is you can assess uniqueness, right? This is kind of like, I wouldn't say an emergent property, but it is a property that is only meaningful with collections of data. Same with monotonicity, your friend's mean, median, standard deviation, classic descriptive statistics, maybe normality checks, chi-squared tests, things like that. Fractional checks to say, I expect 90% of my data to be of some property. And the thing to notice here is that statistical properties, by definition, can only be verified at runtime. I only know whether something is a normal distribution by looking at the actual values. However, we can also define functions that use statistical type annotations that verify valid operations on those types, going back to my type definition in the beginning. And the second term that I mentioned, data testing, I think is a huge component of Pandera. So it lets you validate not only real data, but also the functions that produce them. So in the real world, you have some raw data, you make a schema for that, you validate that. You have a function that then transforms that raw data, you want to also validate that. But in your unit test kind of CI pipeline, you want to generate test cases to make sure that the transform function is doing what it's expected to do. I'll show you a nice feature with data testing, but first I want to introduce you to kind of the syntax and how you define these schemas. So if you've used Pydantic or data classes before, this should look very familiar. Pip install Pandera. And then you inherit from this schema model class. And each class attribute is then a column or a field. You say it's a series. This also supports Pandas indexes, by the way. And you say what type it is. You type annotate it with this data frame, this special syntax. I won't get into too much, but you're saying it's a data frame conforming to the schema. You slap on this decorator. And this is just Python code, right? This has nothing to do with Flyte. But it plays well with Flyte, really well. So all you have to do is install this plugin, import it into your script, and your task functions will automatically use the Pandera spec and validation routines to validate the data. Okay, so that was a very much a toy example, a quick start example. This is a schema for the California housing data type, right? So we can now talk about types for these, multi-field columnar data sets. As you can see, I've put the latitude, longitude constraints that I mentioned. And here I'm just putting a reasonable upper bound on, how many average bedrooms can, I think 1 million is pretty good upper bound. And here's our target variable, median house value. How am I on time? I'm good. And this coerce flag basically says, before you apply these validation checks to the data frame, coerce all of the columns to these specified types. So you won't have to call as type or manually coerce the columns anymore. Now, one thing I want to highlight here is this. This is actually, I've spent a lot of time trying to think about how to express statistical distributions and statistical checks in Pandera. The initial try was kind of unwieldy and weird, and no one uses it. So actually, in preparation for this conference, I think this is a pretty good way of doing this. And this is a custom check. This is not a built-in check in Pandera. Basically, I'm saying I expect the mean of median house value to be 2.0685. I got that value by manually inspecting the data, exploring it, computing the mean, right? How do I write these custom checks? And this is really the crux of Pandera, is to make custom checks very easy to write. So custom checks are just functions. Ignore this one first. This gets a little complicated, but the mean equals function check takes in this series pandas object and uses the SciPy library to do a one-sample t-test on the series. And the null hypothesis is that the mean of the data is equal to the value argument, right? This value argument. And if you're familiar with statistics, they like a lot of double negatives, so I have to read this out every single time. If p-value is greater than alpha, we can't reject the null hypothesis, so meaning that it's in the expected distribution. This mean equals strategy, this is a way to take the parameters here of value to generate data. And this actually uses the Python package Hypothesis, which is a property-based testing tool. And we're using NumPy here to generate random, this is a random variable to generate data given the parameter of value. We could extend this with standard deviation too, but this is a simple toy example. And this is a syntax to register the custom check so that I can actually use it in the context of my schema. Okay, so I've shown you the basic syntax. I've shown you how to customize it. What do you get? So this is Pandera with Flyte. And this is the Flyte UI. I've intentionally introduced data corruptions here. So again, our poor latitude column is missing again. So this is a Pandera error message. So the way Pandera works is you say schema.validate data frame. It'll return the valid data frame for you if it's valid, tautological, and it'll raise an exception if it finds any failure case. So what other kind of failure cases can you see? So this is complaining that the data is the wrong type. I introduce a bunch of strings here, n/a, and Pandera is saying, hey, I expect latitude to be a float, but I couldn't coerce these values. And again, here, it's telling you exactly where the failures happened. These are the original index values for that data frame. You also know when your data has the wrong values. So this is similar to the previous slide, but this is outside of the range of -90 and 90 for the latitude column. And finally, with our custom mean equals check, you can see whether our data passed that hypothesis test. So now, because I spent so much time explaining what this mean equals strategy is, this is it in practice. So if you've ever despaired at writing, oh, I need to write this, I need to hand code this data frame, mock data frame for my unit tests, well, despair no longer. You can take your schema, call the .example method, and it'll generate data that's valid under your system's, your schema's constraints. Yay. I'll show you how to use this a little bit later properly in unit tests, but all of what this is, all of what I'm trying to say is you can test your data, the functions that produce them. So this is a PyTest unit test that tests the happy path case and then tests all the random data corruptions that I've done. And this doesn't use the data synthesis, by the way. So this is just calling functions where I've introduced these corruptions and I'm asserting, what the expected error messages are. And you can also test the artifacts that they produce. So this is a unit test for my train model function. This is important, so I'll kind of go through each line. basically, I'm using this given decorator, which is a hypothesis library thing. And I'm basically telling it, hey, take this California housing data, turn it into a data synthesis strategy, pass it into my PyTest function, and bam, you have your data. I can call my train model function on it, and then now I can assert properties of my model. I didn't make a schema for the model predictions, but you could if you wanted to. So turns out I'm going to have some time for questions, but the 3 takeaways I want you to take from this talk is that Flyte is an orchestration tool that gives you type safety, and type safety is really deeply integrated with a lot of its features, which provide benefits relating to reliability, efficiency, and auditability. With Pandera, you can ensure the quality of data flowing through your pipelines, and you can ensure the correctness of the functions in those pipelines by expressing statistical types. And finally, if you combine the two, you can build, deploy, and scale these machine learning pipelines while enjoying the guarantee that when things go wrong, and they will, you'll know exactly where the error came from and get some hints about how to fix it. So in the Flyte roadmap, we're going to focus on better reporting. So FlyteDex is a thing we're building to make customizable reports for artifacts and data structures that flow through the Flyte DAG. ML awareness tools, features like inter-task model checkpointing and data labeling, and service serving integrations with many maybe of the tools that are talked about today, integrate with them for model serving. And on the Pandera roadmap, I'm going to focus on extensibility. So support for Xarray, JSON schema, PyArrow, basically kind of like the data container ecosystem in Python. Adding more built-in checks and statistical hypothesis checks, and getting more interoperability with the general Python ecosystem in general. So there is a fast API integration that I'm talking with the author of that to figure out what to do there next. Obviously Pydantic and PyTest as well. And if you want to learn more, here are some resources. I don't know if the slides will be made available. They probably will, but on Flyte, you can go to flyte.org, visit our docs and the repo, and Pandera is at Pandera dev Pandera on GitHub, and the docs cover way more features than I've explained here. And you can contact me at neil.union.ai. My Twitter handle is cosmicbboy. Thanks so much for your attention, and I hope you learned something new today.